Okay, everybody. The choice is cold tea or cold espresso. So, Arnold's lecture dealt with a curved beam experiencing bending. We'd just go over the terms. I think there could be a mistake in the tutorial sheet. So either I've got wrong or Arnold needs to correct the tutorial sheet. So if we go over just how to use the equations for the curved beam part, what are we looking at? So we've got a curved beam like this. Let's make it quite fat actually. Leonardo da Vinci said that you can judge an artist by how well they can draw a perfect circle freehand. So this is going to be my neutral axis here. So in terms of terminology, the first thing to say is the neutral axis is your definition for the radius of curvature we've seen previously for straight beams. We're going to use a big R for that. Just so I can keep track of things, and to remind you, I'm going to put a little subscript NA next to that. The definition for the radius of curvature, I'm not doing any of the proof, that would take 40 minutes, is that we take A for the cross-sectional area, and we find it by integrating with respect to area 1 over R. So 1 over that, then we're going to end up with units of R. 1 over R, as it were. So the R is an arbitrary point from here. So that's my red dot. So R is just an arbitrary point in space. So to keep track of that, R relates to Y. So again, I'm going to use a little subscript Y here just to keep track of the meaning, where Y is defined as the distance away from the neutral axis. I think I probably will tend to work not using Y. I think I'll tend to use little r, not y. So little r is actually given as or rather, I've done something wrong here. So, or rather, we're going to define y pointing away from neutral axis I'm just thinking if I want to be pointing y upwards. And why would I want to do that? Must be a reason why I want y to be pointing upwards. me pause the video and think about it. Okay, so other than that's what it's done in the textbooks, I can't really think of a great explanation. Obviously, y is pointing towards your centroid of this circle, so that's the logical way that you would want to point it. Normally, y would be pointing the other direction for a straight beam, but with a straight beam, you're applying sagging. Here, you're more likely to be having a hogging situation, I think, where the stress is coming more like that. You're more likely to be trying to pull this curved section apart in that sense. So perhaps that's the reason for the definition. Other than that, it's done in the textbooks. We'll go with that. So the RY is defined as the RNA, take away Y. Okay, so take away this distance here, and then we're going to end up with the correct location that we're going to want to be at. Yeah, so if I'm doing a negative Y there, shift it, and I'll get to my right R, little r value. So again, I'm not going to keep this, just so that we can keep track of our meanings. The little r is got a subscript y to refer to the fact that it's some arbitrary y position in space. What other things do we need? So we need E, although I'm not going to use it. Which is given as R bar. So I will call that RC minus big R NA. So the C here is referring to the centroid. If I'm looking at the side, let's exaggerate our problem. So imagine we've got a side section like this. So the centroid will be closer down to the base. Okay. So I think this is the so this is the kind of example you normally would find in a textbook, and your neutral axis would be higher up. So your R neutral axis. So again, we're measuring from some sort of point in space. So what I'm doing here is I'm looking at this side section, and this location is given as that's to the RNA, and this is the little, this is my little RC bar. And again, I've just put in the subscript C to remind me that's referring to the centroid of the problem. Okay, so that took a while, just talking about the positions. Then the equations that Arnold derived was, okay, and I can also talk about the definition for RC. And that's straightforward. So that's given as the cross-sectional area, integrate the arbitrary location of R, so an R variable here, actually I'll just use R. So integrate the variable R over the cross-sectional area. So that's our definition for a centroid. So that's fair enough. That's what we'd expect the same thing for any sort of cross-section. Right. So we got them. The first thing you can derive is that the stress is dependent upon the Young's modulus. Little r, so that's my arbitrary location. Take away the r at the neutral axis. And again at some arbitrary location, times by delta theta over theta. Right, so we've applied a load or a bending moment. We've changed the angle of curvature that's going to fit throughout this this beam. So we've made it we've changed that angle theta somehow. So in a way, when the load is being applied, then that becomes just a static term. Your E for your material is obviously static, and then your stress is going to vary inside throughout the cross section. Okay, so that's the first term that was derived, and then the second term was, where is it? So that was that stress can be dependent upon the turning moment. So let's say we're applying a moment, bending moment, sorry, on this. Divided by the cross-sectional area, the E term, which I'm going to get rid of, and R. So I'm going to substitute in, that's RY. So I'm going to substitute in the this expression above. Don't really see any reason why we want to keep it. Okay, so stress can be related to this term. So this is in terms of the, if you think about your engineer's bending equations, it's kind of like that you end up getting your left-hand column from this expression, and this is your middle column. Well, your the M and the A, that would be your first column, and then you can separate that, and then you're going to get this. So this is the bit that's the one we're going to use most. If we just look at it for the moment, we can see that we've got force times distance here, so a moment divided by a, well, if you could take this term here, you could take the force times distance divided by a distance here, so we've got force, then you can divide it by the area, so you've got stress, and then you can see that you've got this ratio of these two terms which will just cancel out. So you could kind of think of it, if you just look at the dimensions, you could think of it in those sort of terms. The other way you could think about it would be to keep these terms here on the sort of like the right of the equation, because they're going to be your variable terms. The ry is some arbitrary location, and here, once the force on moment's been applied, that's going to be a constant. The area will be a constant, and the centroid and the neutral axis are constant. So you can consider all these to be constant terms. So if you were writing that out, a bit like the engineer's bending equation, you could then separate your m and your a. You would probably want to keep your RC as well. Maybe you want to do it like this. So they are all your constant terms. And then your stress. Right, well, your stress, and then we got some variable terms here, so bring up the I think I'll keep the stress on the left. Okay, so that would be a pseudo start to look like a similar to expression to the engineer's bending equation. And notice, unlike the notes, I'm using r's and not y's. And then you could arrange this expression here, which we're not likely to use in problems, and then tag that on as the final bit of the column. So I can see bringing my ry up, my ry take away neutral axis down, then that leaves me with E delta theta over phi. So that's a little bit different to the expression that Arnold's got in the notes. So I'm not 100% sure whether that's correct. It does look a little bit more elegant. So we've got constant term here, like in the engineer's bending equation. Here we've got the stress. Obviously, here you've got a force times distance, and you're dividing that by an area and a distance. So you've got stress variable, stress dimensions there. Here again we've got stress dimensions, and here we've got stress dimensions. Young's modulus, remember, is measured in pascals. So yeah, so that takes us up to the tutorial notes. So we got a slight difference in the expression, so I'm not too sure about that. Right, let's leave that there.